general course announcements, then we'll get into the details here. Okay, so it looks like I do have the recording started. So today we're going to be pushing into our new topic, which will be chapter 14 of your textbook. But the other big things that are going to be happening this week is in our lab period. So either Tuesday or Wednesday, we're going to be taking exam number 1. Now, in terms of exam number 1, I will be providing you the exam document. I'll be providing you the equation sheets, and if you need any lookup tables, I will also provide those. So those will be the things that I will bring to the exam period. You are going to be responsible for bringing your pen, pencil, eraser, and then a calculator, again, one that meets the standard of the class, so basically the 2-line calculator. Those will be the things that essentially you will be required to bring. Make sure that you are prepared. In terms of being prepared for the exam, there is a small little review section on Canvas. So I created a exam 1 study material module, and then there's a page. The page should have a study guide, just a reminder, and of a bullet points of some of the key topics that we've covered in the first 3 weeks. And then I pulled a few select problems from some older exams, so it gives you some idea of kind of some old exam questions. Now, your exam would be slightly different, but again, those are just some practice problems, just kind of see how I might phrase some of the questions. Again, those are all provided in the exam study materials. Numeric solutions were provided for each of the exam or old problems. So take a look at that. Again, that is on Canvas. So make sure that you do use those resources. Let's see, otherwise, the CFR Engine Lab, you still have a week out for that. So again, that will be due next week, so not this week. So the main thing this week is to study for the exam itself. All right, so I think that covers the exam and study materials. So again, if you have questions about that, do let me know. But the exam itself will cover, I guess the last thing I want to point out, it will cover the material from week 1 and 2, our auto, dual, diesel cycle combinations, and then kind of the preliminary gas mixtures that we talked about last week. So basically consider homework 1, 2, and 3 available for the exam. And so that will be your main focus. Okay. Otherwise, if there's not any questions on exam or exam procedure, I'll go ahead and begin. Just a reminder, though, the exam will be in person in our lab period. So again, make sure you do show up to lab this week, because that's when you're taking the exam, and it will be administered in SG01. So just if you have any questions that you want to ask outside of class, feel free to just send me a message. Otherwise, at this point, we will begin our new topic, which is going to be chapter 14 from the textbook, and that is psychometrics. Now, psychometrics is going to be building off of what we started last week, which was our ideal gas mixtures. And so before we get too far into this topic, we first need to figure out what is psychometric. What does this term mean? And so the basics of psychrometrics is basically going to be a gas mixture, but it's going to be focused on a very specific setup. And that setup is we're going to be looking at dry air, so air that we've used before, and we're going to be mixing that with a vapor, and that vapor is generally going to be water. So we're going to have air and water vapor as an ideal mixture. And so if you want to think about that, that's basically your humidity. So this is going to be dealing with a lot of HVAC type setups where we have humid air and we have to do all of the calculations. And so this is to deal a lot with kind of atmospheric science as well. And so again, all we mean by psychrometrics is the study of dry air and water vapor for most applications. Now we could do some different mixtures. I think you will have a homework that eventually deals with a different set of mixtures, but most of the time whenever we say psychrometrics, we're going to be referring to air and water vapor. Now, to make sure that we kind of keep our terminology straight, we have to kind of go over a few terms that we're going to be using throughout this next 2 weeks when we're studying psychometrics. Now, the basis of this is to keep track of how are we going to be modeling the air. And so the kind of new term that we're going to look at is we're going to talk about the air having moisture content. And so we'll refer to any sort of psychometric mixture as moist air. And so moist air will be this term that we called dry air. Dry air would just be air as we've considered it up to now. We've basically said we had that as a lookup. We could get a specific heat. We could do a table lookup if we had variable specific heats, but we said that was just an ideal gas. And that was that setup that we had before. Now, whenever we look at that, we're going to call that same setup, that same model that we've done before, dry air, and moist air is now going to be this combined mixture of air and water vapor. Now, when we deal with moist air, we're generally going to assume that it's going to follow the rules for an ideal mixture. Now, the ideal mixture meant that we had to assume both air and water are going to behave as an ideal mixture, which means that both of them have to be themselves kind of an ideal gas. And so if we think about that, we said, well, air, that's easy. We already made the assumptions up until now that it's an ideal gas. Why change? That worked. So we can say, okay, if that was an ideal gas up to this point, it's still going to be an ideal gas. But whenever we dealt with water, steam, well, those were always table lookups. We said that was a very complicated equation of state, and we generally weren't able to use an ideal assumption for steam or water vapor. Now, what we're going to do is we're going to do a little bit of hand wavy stuff here, but it all works out. And that is, we said, well, if we thought back to last week when we talked about mixtures, and we said, well, they had partial pressures. And so if we think about the amount of water that's probably going to be in air, we said that's probably pretty small, which means our mole fraction is pretty small, which means our partial pressure is pretty small. And we said, well, if the pressure of the water vapor in the mixture is going to be pretty small, well, then we could kind of get away with treating it as an ideal gas, because one of the criteria we had was that the pressure of the gas had to be well below its critical point. And so we said, well, if we have a low enough pressure, we'll be able to assume water vapor can kind of be assumed to be an ideal gas, because for water, we can say, well, the critical pressure is going to be about 3.77 megapascal, so very high critical pressure. But for most engineering purposes, when we deal with psychometrics, it's going to be about atmospheric pressure, because that's where we deal with kind of humid air the most. That's our most common assumption. So if we deal with it about 1 atmosphere, that's about 101 kilopascal. So that's well below the critical pressure. Plus we have to take into account that it's going to have a partial pressure of that. So we're talking very, very low pressures. And so again, ideal gas will work for water vapor in this case. Now, when are we going to be applying this assumptions, and what are the kind of applications that we're going to be eventually getting to once we get kind of our basic terminology down? Now, the common applications of this are going to be related to the heating, ventilation, and air conditioning field. And the common kind of analyses that we're going to be able to do are going to be related to heating and humidification. So if you want to keep your building warm during the winter months, well, you're going to have to take your outside air, you're going to have to heat it. But when you heat it, it's not always going to be really comfortable. And so we have to talk about human comfort. For human comfort, we want to have a little bit of humidity. And so we have to also humidify the air. We have to put some water vapor into the air for our own comfort. And so that's one application. The opposite would be cooling and dehumidification. That will be another process that we will talk about. And then another fairly common interaction for this, or application for this, would be a cooling tower heat exchanger. And so we saw one of these actually in week 2's lab, our first actual lab, the chiller lab. When we tried to reject heat out of the building from the chiller, the water line was routed up to the roof of the building, and we had a wet cooling tower. A wet cooling tower is going to use psychrometric. It uses essentially the energy of the fluid going through phase change, and we're able to model it using some psychrometric. So that would be the concept of the wet cooling tower, is going to be able to be kind of determined using the kind of models that we'll discuss in the coming weeks. Also, it should be noted that other common applications of this is just atmospheric science. So whenever we're dealing with atmosphere, we want to know what the weather is. We also generally want to know what the temperature, so we want to know what the temperature is, and we also want to know the humidity. So like in the summer, if we're going to go out and do something, well, we want to know both of those, because if it's a dry heat, well, that might be a little bit better. So you're in the middle of like Arizona, maybe a desert, well, it's going to be a dry heat. Or, you know, so like 100 degrees there might not be the same as 100 degrees in, say, Florida, where you're very near an ocean. You might have high humidity. Those two different locations will have very different feels for maybe a similar temperature. And so that is another common application. Now, this is where we're going to be going. Today, we are going to be kind of covering some of the fundamentals, and we're going to then build from that point out. Now, in terms of the fundamentals, we note that this is going to be a mixture of two different gases. And so we are going to fall back on last week's material. We're going to talk about this as an ideal mixture. And so we have to go back and just pull out some of the rules that we used for gas mixtures and set those up so we're ready to essentially apply them as we work through kind of the new content for psychrometrics. Now, in terms of the old contents that we want to come back to, we want to remember Dalton's law. So Dalton's law, when we talked about last week, that was our law of partial pressures. And we said we could use that to say all of our individual component pressures have to sum to the total pressure. And so in our case, we're going to do that. We'll say the total pressure is equal to the sum of the air pressure. So this would be the partial pressure of air. And then we also have the partial pressure of our vapor. Now I'm going to use the subscript A. This is always going to be used for air in these chapters. So for the next 2 weeks, sub A stands for air. Subscript V stands for our vapor, which is going to be our water vapor generally in the air. Now, in terms of our mixture composition, we're just going to treat air as its own ideal gas. That way we don't have to do the individual component by component analysis for the air. We're just generally going to use our base mixture for air. We're not going to have to try and account for our nitrogen, our oxygen, and all the other trace gases we have. It's just making our basic air model for this will work. And again, that keeps it a little bit simpler in terms of our models that we want to actually do. So we're going to, again, just have the two components. We'll have our total pressure, and that will just be the sum of our two individual partial pressures. And so again, these two values are our partial pressures that we used before in last week's lecture. Now, in terms of calculating the partial pressures, well, we're able to make those calculations because both of them are now going to be an ideal gas. And so if we note that they're both going to be an ideal gas, we said, well, we have an equation of state, PV equals mRT. And so using Dalton's law, we can say, well, we wanted to get the partial pressure, so we had to fix the temperature at the mixture temperature. We had to fix the volume at whatever our volume container was for the system. And then we were able to solve for the partial pressure of each component. And so I want to note here, temperature and volume for both of these are going to be the same. So T and V have to be held the same to allow us to use the idea of partial pressures, which was Dalton's law. So again, those are constant for both cases. Now that will come in and be important here as we move forward, which is why I wanted to point that out at this point. Okay, so those are going to be kind of some of the key things that we will talk about, we're going to be using moving forward, but there's also one more part, and that was when we took Dalton's law and we did a little bit of the ratios of our partial pressure over our total pressure, we were able to show that, well, we could take a mixture of ideal gases, and that itself could behave as an ideal gas. And when we did all of that, we said there was an important relationship between the partial pressure ratio, or that fraction, and the mole fraction. And so we're going to be using this concept now to also relate our total pressure to our partial pressure using the mole fraction. And again, this is going to come back and be very important moving forward. So in terms of our mole fractions, well, we'll have the partial pressure of the air. That'll be the mole fraction of air times the total pressure of the mixture. And we can repeat this for the vapor. So once we know the mole fraction of the vapor, we have our total pressure. We could get the partial pressure of vapor. And so you generally, for most engineering applications, total pressure, that's going to be like our atmospheric pressure. So about 1 atmosphere. And so once we were able to figure something else out in one of our mole fractions, well, we could then go ahead and work to our partial pressure. So again, this is going to be really important for our analysis to be able to move between total pressures and partial pressures, and then also be able to apply Dalton's law for those calculations. Okay, so that is the old material from last week. Now we want to go ahead and put that to use this week. But to do that, we have to kind of figure out what is going to be so different this week from last week's lectures. And so the easiest thing to kind of think about is what separates psychometrics from the ideal gas mixtures that we were talking about. It is the fact that if we do enough of a change, we can actually induce a phase change. We can get the water vapor to condense out of the air. And so that's kind of the big picture change that we need to kind of keep in mind. And this can cause quite a bit of complications in terms of our calculations. And so it's always good to try and make sure that we do keep a pretty good fundamentals on kind of the psychometric calculations. And so again, water condensing, we think about that. If we have a cold surface, we can get water to come out. If we have a large temperature change in the air, the water content in the air will also change, and there will be condensation. And so we need to figure out, how do we essentially come up with a way of determining what's the maximum amount of water that we can have in the air, what is our actual partial pressure, how can we essentially make these kind of determinations. Now, the easiest way to kind of think about this, again, is going to go back to our phase diagrams. And so in terms of our ideal gas mixtures, we weren't able to really do that because we were very far off to the right on any sort of phase diagram. Now we're going to be able to bring back our TS diagram. We're going to be able to bring back the vapor dome. And so we will be able to use this TS diagram to kind of help us figure out what's going on in terms of these mixtures and whether or not we're going to have water that is going to condense. Now, in terms of setting this up, what we're going to want to do is we're going to want to say, well, we know that we're going to use Dalton's law for partial pressures. We've noted previously that was going to be very important. And so in terms of Dalton's law, we said, well, that meant the temperature of the mixture had to be the same as the two individual components. We had to have the same temperature for each component as the total mixture. We had to have the same volume. Now, what's really important on the phase diagram is the fact that that temperature of the mixture has to be the same as our individual component. And so this is, again, just looking at the water part of the phase diagram, because water is the part that will have the possibility to undergo that phase change. And so if we go ahead and say, well, we know that we have some temperature that we can measure. And so this is the temperature of our mixture. And so we know that on a TS diagram, we can just go ahead and draw a kind of dashed line like this. And we said our state point for the water, our partial pressure of the vapor, has to lie somewhere on this line because of the way that we defined it in Dalton's law. Now, what we can do is we said, well, if it's on this line, we know that we're going to be dealing with water as a vapor. And so we will probably want it in the superheated region somewhere. So we said, well, that means it's going to be out over here. So let's just go ahead and draw our state point right here. It gives us a little bit of room. And we said, all right, what do we need to establish this point? We needed generally two properties. Now, the other property that we're going to want is we want to talk about the partial pressure of the vapor. And so what I'm going to do to get that partial pressure of the vapor So we're going to go ahead and draw another dashed line here. And once we hit this point, we said, well, if we drew a line of constant pressure, it would go up here through our point. And we said, well, what is this line? Well, this line was a line of constant pressure. That was the pressure of the vapor. So partial pressure of the vapor is this line here. Okay. And so we see that this is going to be in the superheated region. But we said we wanted to now compare it to what is the maximum kind of amount of water that we can hold in the air. And so if we do this, we said, well, let's just kind of do this at the given temperature, because we said for a mixture, that temperature had to be constant. And so if we look at this, we said, well, for temperature remains constant, we're probably going to want to compare it to a saturation condition, probably this saturation condition like right here. And so we said, well, all right, that is going to represent our saturation condition. And we said, well, the saturation condition, that is going to be the maximum amount of water that we can hold in the air at a given temperature. And so, again, this is going to represent the kind of theoretical amount of air or water that we could get into the air. And so to do this, we said, all right, well, this is going to represent the vapor, or so basically our saturated vapor line. So if we remember, this would be a saturated vapor. And in terms of our lookups, well, in the tables, we had a F side of the table and we had a G side of the table. And so what we're going to do is we said, well, if we think about this, well, we're to move from this point to this point, well, we'd probably have to add some water. And so we said, okay, well, to make this move from this point to this point, well, we are going to want to add some water into this system. And so to do that, well, what would change about this system? And so if we think about what changes, well, this point has to converge here, which means that this partial pressure line is going to change. And so this line would eventually start moving up. So inside the vapor dome, this would move up. Over here would be moving to the right to keep that point here. Now, if we move all the way to that point, well, we could say, well, we could draw another line of constant pressure right here. And this would represent the saturation pressure at the given temperature of our mixture. And so what we want to do is we see, well, we have our vapor pressure, we now have the saturation pressure. We only want to eventually kind of head towards this point of the essentially saturated vapor condition. We said, well, what is changing? Well, we have P sub V that is going to change. And so we said, well, let's go ahead and think back to this. We said P sub V, so is equal to the molar fraction of our vapor times the total pressure of our mixture. And we said, well, if we're thinking about this in terms of kind of atmospheric science, well, if we're putting a little bit of water into the air, the pressure really doesn't change that much. It stays about 1 atmosphere. So if we keep the mixture pressure constant and we want to now increase the partial pressure of our vapor, well, we said, well, this value we want to go up. And so that means to do that, we have to also increase the mole fraction of our water vapor. If we increase the mole fraction of the vapor, well, this would mean that we have to increase the number of moles of our vapor. And if we increase the number of moles of the vapor, we'll increase the mass of the vapor. And so if we move this point towards the saturation condition, we will be adding essentially water into the vapor state. And so we said, well, if we went all the way to this point, this is now going to represent the maximum amount that we could have at this point. That would be based on the saturation pressure at the given temperature. Now, in terms of some nomenclature, well, we generally could say, yeah, we can look up P sat, but for keeping things a little bit cleaner in terms of our nomenclature, we will go ahead and refer to this as P sub G at the given temperature. Now, what is P sub G? Where does that term come from? Well, remember P sub G, we said G represented the vapor state in the table. So when we wanted to look something up like the enthalpy on the vapor side of the vapor dome, well, that was always subscripted G. And so what we're trying to say here is that, yes, it's the saturation pressure at this given temperature, but we only want to go to the superheated or the saturation vapor state. We really don't want to get into the two-phase mixture, because if we start to go further to the left, that's where we're going to start having water come out, because we have a two-phase mixture here, which meant we have some water in liquid form, some water in vapor form. Once we get inside the vapor dome, that's where condensation will begin. And so if we think about our rules now for if it will water will condense, well, that means if we have the partial pressure of the vapor that somehow is greater than or equal to, we'll just go ahead and use Psat at this point. Well, if it's greater than that point, well, this would be our line of constant pressure. That would mean it'd have to be over here. And so that means technically our point would be on the liquid side. I said, well, if that's true, we wouldn't have any vapor. And so that means that the water would have to have condensed out. And so if it's also equal to Psat, that means it's probably somewhere in the two-phase region. We already have a little bit of water condensing. And so if this statement is true, water will condense. And so that will now be our check, as we have to compare our partial pressure of our water vapor to the pressure at the given temperature from our steam table lookups. Now, alternatively, we could also write if the partial pressure of our vapor is now less than or equal to the saturation pressure from the table at the given temperature, water will remain in the vapor. And so again, it's going to be driven now by the concept of our partial pressures. We're going to use these concepts to try and figure out what's going on inside of our system. And so again, if you need to kind of visualize what's going on, I always suggest that you draw a TS diagram. You try and do something like this to determine your state and how you can affect what's going on by moving in different directions. Now, in this case, what we did is we did it for a given temperature. But let's say we went ahead and changed the temperature. So let's go ahead and drop the temperature. And we said, well, we figure if we can drop the temperature of the mixture, we could also get some water to condense. So if we cooled the air down, there's a chance we could get some additional water. So is that a feasible way? And so if we go ahead and just kind of draw this out again here, we have T mixture 2. And so if we go ahead and draw another line, something like this, in this case, we will have our state 2 being right here. So again, if we didn't change the amount of water in our system, so we just essentially change the temperature of the air, well, we would move along the line of constant vapor pressure. So we'd end up here at state 2. And in this case, well, if we wanted to see how much cooler we'd have to go to essentially make a phase change, well, we're still going to compare it at the same temperature. And so whenever we're going to make a comparison, if there's going to be condensation at this point, you will always use the value at the given temperature. So this would now be our new, I'll just go ahead and quickly draw this. This would now be P sub G, we'll call it 2, and this would be a function of T2. And so again, what I'm trying to show here is whenever we do a comparison, you're always going to be using your temperature that you measure to determine what the saturation condition is. Now, in this case, we cooled it. We see that we're closer to the vapor dome, but we didn't quite go all the way down to that point. Now, if we continued cooling it, eventually we could hit the saturation condition, and in that case, we would then start having condensation. And so we have to be mindful now of how we're going to change things, how things are set up in terms of psychometrics. Now, goal is we're going to eventually go ahead and work a problem. We'll be able to relate some of these together. But the key thing to note is whenever we talk about P sub G or P sat, again, it's along the temperature line on the TS diagram. And so again, the saturation condition, just to go ahead and clarify this is going to be the vapor pressure has to then equal P sub G. And so that would be at the given mixture temperature. And so we could either do that by adding more water to move our vapor pressure up to this point, or if we dropped the temperature, we could get down to here. So both of these would be saturation points for different processes for our given drawing that we have. Okay, so that is kind of explaining what we're going to be looking at, but in terms of discussing the concepts that we have here in terms of key parameters and what happens when we do things for calculation, we have to introduce some new definitions. Now, those two definitions that we're going to focus on, you may have heard of at least one of these, but these are going to be the two that we are going to spend most of the time for the next 2 weeks focused on. Now, the first one is probably the most important parameter for engineering calculations, and that is referred to as the humidity ratio. Your textbook will show it as kind of an omega, or simply we'll kind of just show it as a W, because my handwriting, it's kind of hard to see the difference between an omega over a W. So in our nomenclature, those are going to be basically interchangeable. Now, this is going to refer to the humidity ratio, as I call it. Your textbook also uses a separate name for it. It has the same meaning. These two are interchangeable, and that will be the specific humidity. So I believe your textbook will use both of those. I generally stick with the humidity ratio for this because it helps me remember what you're actually looking at. Now, what does the humidity ratio actually compare, and why is it going to be so important? And so the answer to that, well, we have to figure out what that ratio that it's going to be talking about. And so if it's a ratio, we realize that it's going to have two components. Something's going to be in the numerator, something's going to be in the denominator. Now, what we found is going to be the most useful for analysis is that we define the humidity ratio as the mass that we have of the vapor divided by the mass of the dry air. So M sub V divided by M sub A. Now we could do this again in flow rates as well. We'll get to that point eventually, but the ratio here again is essentially how much mass we have in the vapor state for our vapor and how much of the mass is of the dry air. Now, what we want to do is we want to go back a few slides, and we said, well, mass, that's part of the ideal gas equation of state. So we said, well, going back a few slides, we had PV, this is equal to MRT, and so we could go ahead and solve for this. We said, well, that would just be M is equal to PV over RT, and we can go ahead and substitute in our partial pressures for that. And so on the top side, if we do this for the vapor, we said, well, that would be pressure, partial pressure or vapor, volume of the mixture over R of the vapor, T of the mixture, because that was how we set it up for Dalton's law. And so writing this out, what we find is we have the partial pressure of the vapor multiplied by the volume that we have for the system, then divided by the gas constant for our vapor times the temperature, and we'll note that that is of the mixture. And then we have that value, and then we can repeat this for air. So we have the partial pressure of air times the volume of the air divided now by R of air times T of the mixture. And so again, this is where that gas mixture calculation comes into play. Now, what we'll note is to get Dalton's law to work, we said, well, that had to have the same volume and same temperatures. So since it's a ratio, those are going to go away. And what we're left with now is we have, this is going to equal the partial pressure of the volume, or volume, the vapor state, divided by the partial pressure of the air. Now, we have 1 over our vapor, so what we have to do is we have to flip the second ratio. So this is our air divided by R of the vapor. And so we can see that there's this ratio that we're going to have to contend with. Now, what we're going to do is we're going to go ahead and play one more trick here, and then we'll see what happens. And so the next trick that we want to do is we said, well, our gas constant for any gas, this will equal the universal gas constant divided by now the molecular weight for that substance. So we note that we have R for both air and vapor. So we can go ahead and do one more extension on this, and that is the partial pressure of the vapor now divided by the partial pressure of the air. We said, well, now do air, so that would be R universal. And we said, well, if we do that for the vapor state, we'll have R universal down here, R universal. Those go to 1. And then now we'll have, well, air would be 1 over molecular weight of air. And so that would put that in the denominator, so molecular weight of air. And then we have molecular weight of the vapor. And so just to kind of clean this up, what we'll have now is the molecular weight of the vapor divided by the molecular weight of air. And then we have the partial pressure of the vapor divided by the partial pressure of the dry air. Okay, so that looks good. We'll maybe make a note of that because you're going to have to do something kind of similar to this for one of your homework assignments. That homework is actually next week's assignment. So you will have to come back a little bit to remind yourself of this definition. So we'll call that air for right now. And then this will be P of the vapor divided by P of the air. So I'm going to box this so you guys remember this for the homework that is going to be assigned next week to come back to this point. But what we want to do is we want to take this a little bit further because there's going to be fairly common themes that we see moving forward. And that is, for most cases, you will be assuming that you have the vapor. Well, the vapor we'll assume is going to be water vapor. So we know the molecular weight. That's going to be 18.015 kilogram per kmol. And we'll also have the molecular weight of air, and that is 28.97 kilogram per kmol. So for the most part, like we said kind of earlier, whenever we deal with psychometrics, it's probably going to be air and water vapor. And so if we have these molecular weights and we have this combination, we can go ahead and do the calculation of the molecular weight of the vapor divided by the molecular weight of air. And doing that and doing just a little bit of rounding, this comes to be 0.622. And so the form that we will use now for our humidity ratio, we'll substitute that ratio in over there. And the more common form that you will see on all of your homeworks is that the humidity ratio is equal to 0.622 times now the partial pressure of the vapor divided by the partial pressure of air. Now, while that helps us a little bit, well, we still have to know what the partial pressures of each of our components are. That's a little bit hard to do. And so we said, well, when we deal with atmospheric science, we said, well, it's atmospheric. That's like a known pressure. That's like 1 atmosphere for the most part. If we think about air inside of our HVAC ducts, pretty close to atmosphere. Think about any air that's exposed to outside of the building, for the most part, to atmospheric. Could adjust it a little bit based on elevation, but said, well, that's probably atmospheric. So if we kind of said, well, that's going to be something that's going to be easier to measure as our total pressure, we can recall that, well, we could take the total pressure from Dalton's law. That would be pressure of the atmosphere plus the partial pressure of the vapor. We can go ahead and solve now for the pressure of the air. This would be the total pressure minus the partial pressure of the vapor, and we'll substitute that back in. Now bringing it all together, here's the final form of the equation. The humidity ratio is equal to 0.622. Now times the partial pressure of the vapor over the total pressure of the mixture minus the partial pressure of the vapor. Now this will be the most common form that you will need to use on homeworks and exams. So this is the equation that you will need to know. Now, when we talk about humidity ratios, there's one extra thing that I wanted to point out. Because it is a ratio of a mass of the vapor per mass of dry air, the standard units on this guy will be in SI. It'll be a kilogram of the vapor divided by the kilogram of dry air. Now that's standard, and if you want to think about it in SI, be pound mass of the vapor per pound mass of dry air. So that's generally the standard accepted way of doing this. But that value is pretty small. So most of air is just air, and water vapor is a very small percentage of the total mole or even mass ratio here. And so this value ends up being quite small. And so, while this may be the general form of the solution, when we get to the psychometric chart, which was going to be kind of a useful tool for being able to calculate some of these, you will have to pay attention, but because to avoid small numbers, they will now do a gram of vapor per kilogram of dry air. So why am I pointing this out? It's because units pay attention to how you're setting this up. Now, for the most part, this will be the default calculations. You put numbers in your calculator. This is what will come out, kilogram per kilogram. But if you're going to be using an external reference, like we will on some of the later homeworks, pay attention to the units, because sometimes it will be a gram per kilogram, which is really confusing. But it is done so that they don't have to print out so many small numbers and clutter up a plot. So that is my note on the humidity ratio. Now that's the first term. Again, this is going to be more useful moving forward, but in terms of a term that we're probably more familiar with is the relative humidity. So this is going to be our second of the key terms that we're going to need for this term. Now the relative humidity is a relative value, and so where this was a ratio of values, this is going to be something that has a set high and low point. And so this value, which is going to be denoted here by phi, this has to be between 0 and 1 for all cases, because it's going to be a relative scaling. Now, I do want to point out that this is going to be used slightly different than the humidity ratio. And we're going to combine these two terms together. I don't want you to get these two confused, because, again, the way that they're set up, there's some similarities, but the differences are very important. Now, what is the similarity? Well, relative humidity, we want to talk about how much water is in the air versus the maximum amount of water that we can get in the air. So it's still going to be a ratio, but we're comparing something that we have to something that's theoretical max. And so to do that, we said, well, we would probably just go ahead and have the mass that we have in the vapor state, so M sub B. We said, well, we're going to want to compare that to the theoretical max. And so if we go ahead and just say, well, let's go back here, slide. We said, what is the theoretical maximum that we have at this point? And so if we have this state point out here, what's the most amount of water that we could get to this into this system before it starts to essentially condense and we can't add any more water? I said, well, that means we'd move along here to the left. We'd reach P sub G, our saturated condition at that temperature. And so we said, okay, if we called that now P sub G for that temperature, let's go ahead and now call the amount of mass that we'd have as our maximum. Call this now the maximum at state G. maximum at saturated vapor condition. And so we'll note that this is the saturated vapor state. And so again, this is going to be a function of the given temperature. So again, we're going to use the known temperature to do this. Now we said, well, before we realized that it was going to be two ideal gases. In this case, we're going to be comparing two things with an ideal gas. So we'll be able to do something similar. So we'll have the partial pressure of now the vapor times the volume divided by R of the vapor times T of the mixture. And we said, well, if we want to figure out the maximum state, we said, well, that was just going to be P sub G now. So we let P sub V get replaced with P sub G. That's going to be our max condition. That's what we just saw in the previous slide. And so we'll make that substitution here. So we say P sub G times the volume, R sub V times T of the mixture. And we realize basically everything is going to cancel. So volume cancels, R cancels, T cancels, because this time it's of the same substance. So we're comparing vapor to vapor. So what this ends up giving us is we have now the partial pressure of the water vapor divided by the saturation condition at that given temperature. So again, both of these values have the same temperature. And so when we look this up, we just have to now look up the saturation condition at that temperature. And so this is going to be the form that's most useful, though I will point out that we could relate this to mole fraction. So we could have mole fraction of the vapor divided by the mole fraction at the saturation condition. But we'll just go ahead and say, well, for now, we really want this pressure ratio right here. And so the form that we're going to use for relative humidity, technically it's a mass ratio here, but the relative humidity for all practical purposes will now be the partial pressure of the vapor divided by the saturation pressure at the given temperature. This will be a slightly off red here. Okay, so that is going to be the key form that we have. Now, why was it important to kind of keep these straight? Yes, they're both mass ratios. One of them is, again, comparing the mass of the vapor to the mass of the air. The other one is going to be comparing the mass of the vapor to the maximum amount of vapor that can be at that state. And so that is going to be the key difference there and the difference in these results. Now, in terms of being able to combine these, we said, well, these two are going to be probably the most important relationships that we're going to be using for the next 2 weeks. And so we're going to probably want to be able to move between them. And so if we recall the humidity ratio, that'll be 0.622. We'll have P sub V over P total minus P sub V. Then we have the relative humidity, P sub V divided by P sub G. And so what we can see here, the best way to combine these will just be to substitute in for our partial pressure of the vapor. This will become Phi P sub G. And so if we make these substitutions, what we end up with is being able to solve for the humidity ratio, which is going to be 0.622. times now the relative humidity times the saturation pressure at the given temperature divided by the total pressure minus the relative humidity times P sub G. So this will be one form of the useful combination. So if we know the relative humidity, we can say, well, if we know the temperature, we're able to calculate the humidity ratio using our knowledge of the system. We said, well, if we knew the opposite, we could do that. Now, to do that, we have to do a bunch of algebra, but the result of the kind of reverse calculation here is we can calculate the relative humidity if we know the humidity ratio, and then we multiply by the total pressure, and then we divide by 0.622 plus the humidity ratio times P sub G. And so these are going to be the two ways to relate one of the known kind of parameters that we have to the other. Now this top one will be the more common one because we'll be able to get a relative humidity, and then we'll be able to convert that directly into the humidity ratio when we need to actually apply it for calculations. Now, where we're going to go with this is we're going to be able to get this into our kind of engineering modeling parameters. And so we'll pick up this in class on Thursday. We'll deal with the properties. How do we deal with properties? How are we going to use this? What are the key temperatures? So we're going to redefine some temperatures. And then we'll go ahead and work an example problem on Thursday relating all of these concepts together. So again, today was more about trying to set up the fundamentals, trying to figure out what's going on in terms of the system. And so that is where we're going to end today's lecture. So I'll go back here just to make sure everyone has a chance to see what the equations are. So if you do have any questions, please let me know. Otherwise, I will see you either tomorrow on Tuesday or in lab on Wednesday for the exam. Again, make sure that you study. Reminder that there is the resources on Canvas. And again, there's also going to be homework that is due tonight for chapter 13, which is the gas mixtures. So if you have any questions about any of that, please let me know. Otherwise, that is the end of today's lecture. Have a good evening, and I will again see you in lab for the exam.